Today's section is 5.3, rate of change and slope. So rate of change and slope. And first thing I want to say right out of the gate is that those two are the same. So whether we're talking about rate of change, we're talking about slope, those two things there, maybe put an arrow to both, that they're the same thing. And if we're talking about the slope of a line, it's really saying how fast the line goes up or down. So how fast the line goes up, and maybe I'll say or down in parentheses. And if we have a line that's going up, so we typically look at a graph as we're going across to the right. So if we have a line like that, it's going up, it's going to have a positive slope. And if we look at a graph as a graph goes to the right, if it's doing something like that, then it'd be downward, and that's going to have a negative slope for that. Now the actual equation for slope then, we're going to get to in a section or two, where for now I just want to write it this way. So slope, and this you saw last year in my class at least, slope was rise over run. And we're going to kind of add some things to that, look at that a little bit differently than we did in 8th grade, or in 8th grade math. And the rise we're looking at, well, if I look at a couple points on this graph here, and if we were trying to figure out how much does it rise between those 2 points, we're really saying how much does it go up, or what's the change in the y values. My first point had a y value there, my second point has a y value there. We're saying, what's the difference there? How much does that thing there go up? So it's the change in y. So the rise is really just the change in the y values. The run was, well, how much is it going side to side? We talked about running. It's easiest to run on horizontal ground. So run is doing the side to side there, which would be the change in the x values. So change in x. And I want to throw one more new thing to you, and that's going to be this here, that there's a Greek letter, it's just a triangle, that's the letter delta. Now I'll maybe write out the name. So as you hear me say delta, you kind of know what I'm talking about. But that Greek letter delta, the triangle, stands for change in. So change in. So if I were to talk about like delta t, it's the change in t, the change in time. Well, if we take and apply that to our equation up above, we said that the rise is the change in y. So one way that you could write that that's shorter is just a little triangle and then a y, or delta y, which becomes a change in y. And change in x is going to be similar. It's the triangle, it's the delta x, gives us the change in x. So maybe pause the video a sec if you need to copy some of that down, and I'm going to flip to an example. So my first example now is going to be looking at a data table. So let's say I have an example, and the question's saying find the slope of the different segments in this data table. So find the slope. And I'm going to have two things. One is going to be age. It's my independent, that goes on top. And then my y values, my dependent, are going to be the shoe size. I tried thinking back to what were my shoe sizes back when I was in middle school or early high school. I'm going to say when I was 14, I think I was about a size 10 when I was 14. Think of my first running shoes, my Brooks Horizons. And so that there. And then from there, when I was 16, I went up to a size 11. And then when I was in college, when I was age 20, I still stayed at size 11. So I maybe shouldn't take some of the challenge out of it, I suppose, but you could look at it if you wanted to, that if I have age, oops, that's supposed to be my age, so we'll say 14 is there. So if I'm doing 14, 16, and then 20 has to be twice that distance, we'll slap it over there. But you could say maybe that's my height of 10, so size 10. And then when I was 16, I was size 11. Then when I was 20, I was still size 11. So if we were to kind of look at that, I'm looking at what's the slope of this line segment here, and what's the slope of this second line segment where my y didn't change. All right, so now looking at slope, first I'll start with what's the slope between these two, between 14 years and 16 years old. So my slope then, to save space, I'm just going to write delta y over delta x. That slope is the change in y divided by the change in x. And in our data tables, we always put the independent variable on the top or in the left column if it's a vertical one, and the dependent in the bottom row or the right column. So my change in y then is going to be here from 10 to 11. So I can say 11 minus 10, or I'll just write in a 1. So I have a change of 1 shoe size. Then my x is going to be looking at what's the change there. 16 minus 14, 2 years went by. So my slope of this first line segment is going to be 1/2. That I went up about a half size every year. Now if I were to do that same thing, or maybe I should say then the slope here is going to be 1/2 for this first line segment. Now if I look at my second line segment, I'll say between here and here. Now what's going to be the slope of this part? So the slope again will still be my change in y divided by my change in x. So my change in y, my shoe size didn't change at all. So 11 minus 11 gives me 0. I had a change of 0 in height on the graph, which fits if we're looking at this segment here. The graph doesn't go up and down any in there. And now my x values, I'm going from 16 to 20. So I had a change in x of 4. As I jump right there, you could also say change in 4. But 0 divided by any number other than 0 is 0. So we find that now if we have a horizontal line, the slope there is going to be 0. All right, pause the video if you need to copy that down, then we're going to jump to a second example. So say you have a graph something like that. If you take and find like a couple points on the graph, so I'm going to pretend it goes nicely through there and nicely through here maybe, something like that. But if you wanted to find the slope on a graph, you could go and figure out points and put them in a data table. But really, if your slope is just rise over run, how much does it go up from one of those dots to the other? You could take and make it into a little triangle if you wanted to write triangle. So the rise is 2 and the run is 3. Yep. Because we're going up 2 and then 3 to the right. So slope is going to end up being 2/3. If you were to take and do that same thing but in the opposite order, if you put your little triangle down here, if you're going from this point here on the right back to the one on the left, we're going to go down 2, right? Do you agree down 2 would be like a -2? So that our rise now is going to be a -2. We're going down 2. But now as we go 3 to the left, going in the left in the x direction is negative also. So you'd have a -2 over -3, which you agree those just cancel out and give you the positive 2/3 anyways. So this here then equals 2/3. So either way you'd have a slope of 2/3. Last bit is this here. The steeper the line, the further the slope is from 0. So steeper the line, the further the slope is from 0. And I'm just going to throw a bunch in here. If you know this, again, skip it if you want to, but something like this, small slope, big slope.
Pretty small.
Small, is it positive or negative?
Positive.
So small positive, and if you want the concrete, you could, it's maybe something like 1/4. You know, it goes up 1. Every time it goes over 4, it goes over a lot faster than it goes up. If you were to take one and make it same direction but steeper, this is going to be large positive, negative? Positive. And you could maybe say like an example is 3. And again, if you're kind of like, yeah, I could have told you that, and skip it. If you were to do the same sort of things but with negative, a negative is going to just be a gradual downhill. Is that kind of down? We'll make it a little better. But so something like that. So that'd be a small negative. And if you wanted to say like maybe a -1/5 or something like that. Doesn't look quite as steep as my other one. one more that's probably the, so that'd be, now I don't know, do you call it a large? Because it's going to be a negative number that's far from 0 at least, right? So my example maybe then could be like, it's example like -5 or something like that. But I feel a little bit weird saying this is a large negative number. So large, question mark, negative. But it's at least going to be a negative number that's far from 0. Further than like a -1/2 or something like that. Okay, the two that are probably worth writing would be these two special cases. If you have a line that's horizontal, its slope is 0. And if you're not sure why, you could, and you could always make a horizontal line and throw some dots on it and so on, but when you do like the change in y divided by the change in x, kind of like that one example we had, the change in y is 0. It doesn't go up or down at all. So you're going to get 0 over some number. And it doesn't matter if that number is like 5 or 2 or 7. If you cut a pizza into a certain number of pieces and you get 0 of the pieces, you get 0. So 0 over any number other than 0 is 0. Okay. Then the very last one then to hit is, if you were to do that opposite of that, you do a vertical line. So it's supposed to look perfectly vertical. Slope there is
-1.
Maybe let's do this. If we do the change in y divided by the change in x, where do we put a 0 in that fraction? In the denominator, because it's not moving any side to side. It's moving 0 in the x direction. Yep. And any number divided by 0 is what? When in doubt, check your calculator. It gives you an error. It's going to be undefined whenever you have a vertical line. And that's it for